Welcome to the EE-371 electromagnetic field theory class. I am Dr. Arbab Abdurrahim from the Faculty of Electrical Engineering. In the previous lecture, we have discussed an operator called as the curl operator. We have discussed that this is an important operator in the vector analysis, and we have seen that at the end of the discussion we have obtained the curl of the magnetic field intensity, which is equal to the J, and this is also called as the point form of the Ampere's circuital law. So the curl gives you the point form of the Ampere's circuital law, and this is also called as the third Maxwell equation. So this is what we have discussed in the previous class. Now we will continue with this discussion, and we will try to develop or study another theorem called as the Stoke's theorem, and then at the end of this Stoke's theorem we will discuss the magnetic flux density. Now to discuss the Stoke's theorem, let's consider this surface S, which is subdivided into small differential areas, small differential surfaces, and let's say we apply the definition of the curl on each surface. So we will obtain H dot dl for any particular surface. Let's say we are considering this incremental surface, and this will be divided by the area equals to the curl of this vector with the subscript n. Now this is the definition of the curl, that the line integral to the area equals to the curl. And look, we have said that the direction of this is always normal, as the cross product gives you the direction which is always normal to the surface. So we can also rewrite this as the H dot dl ds divided by the surface area, and we can write this as the vector dot the normal unit vector, because the cross product will always give you the direction which is normal to the surface. So rearranging again this expression, we will obtain the we can write this as del cross HS, and we have n del S. Now what is this? Basically this is the direction and this is the magnitude of the surface, as we already know that the surface delta S is having a unit vector or a directional vector which is normal to the surface. So the surface area vector is like always the magnitude of the surface area and its direction, which is always normal to the surface. So we can write this in this form, or simply the del cross H, the delta S. So the dot product of this curl of the magnetic field intensity and the surface area gives you the total current, or is equal to the closed line integral of the magnetic field intensity. Now if we find the circulation of each delta S, this is the circulation of delta S. Now if we find the circulation of each of these delta S and sum the results, now as we are evaluating the closed line integrals, then some cancellation will occur, because each path, this path, will be covered in both direction. For example, if now I consider this in the counterclockwise direction, this path, so this is now another path, this same path, the same boundary has been traversed in both direction, in the up direction and in the downwards direction. So this will cancel out. Similarly, these boundaries will cancel out, these will cancel out. The effect of these boundaries, they will cancel each other out. This will cancel out with this will cancel out with this boundary, and so on. All these interior boundaries, interior walls will be cancel out. Only those boundaries at which cancellation will not occur are the surface boundaries. These paths, these surface boundaries, these will not be cancelled. So therefore we can write this as the line integral, as the closed line integral will become equal to the surface integral of the curl of the magnetic field intensity, and this is called as the Stoke's theorem, which says that the Stoke's theorem relates the closed line integral to the curl of the surface integral, similar to the divergence theorem, which relates the closed surface integral of the electric flux density to the volume integral of the divergence of the electric flux density. So the Stoke's theorem relates a surface integral to a closed line integral, and the divergence theorem relates a volume integral to a closed surface. And both theorems find their greatest use in the vector analysis, in the vector proofs. Now to validate the Stoke's theorem, let's solve this drill problem, which is to evaluate both sides of the Stoke's theorem for the field H having the x component as the 6xy, the y component is minus 3y square ampere per meter, and the rectangular path around the region is x greater than equal to 2, less than equal to 5, y greater than equal to minus 1, less than equal to 1, and then the z equals to 0 plane. So it means that we are talking about the z equals to 0 plane. Z equals to 0 plane means that the rectangular path is in the xy plane. So we can see that the x is changing from 2 to 5, y changes from minus 1. So let's say this is x changing from 2 to 5, y changes from minus 1 to 1. So what we have to do is, for this rectangular path in which the current is in the z direction, or the what will be the surface area or the unit vector of the surface area is in the z direction, which we already know because the area is the rectangular path is in the xy plane, and the unit vector of this plane or the unit vector of this area is always normal to this plane, which is the z direction. So the ds will always be in the z direction because the plane is in the xy plane. So now we have to evaluate both sides of the Stoke's theorem. The left hand side is the line integral, whereas the right hand side is the surface integral of the curl of the magnetic field intensity. So this is what we have to compute. Now we start with the left hand side. So it is very easy now to obtain the left hand side. We apply this closed line integral. We divide this path into 4 paths: 1, path 2, path 3, and path 4. So the coordinates of each path are always given. Here we will add the path 1 plus path 2 plus path 3 and path 4. So for the path, we will start with path 1, that is the h dot dl. This will be equal to the integral of this path 1. So this, we always move the counterclockwise. So the limits are from, as the x is constant, and the limits are in the y, that is from -1 to +1. And remember, we will again have the h, which is 6xy ax minus 3y square ay dot the ds. Now what is the ds, sorry, the dl? What is the dl of path 1? So dl1 is the change in y into the ay direction. So we can write this as dy ay. So again the limits are -1 to 1. The dot product will give you minus 3y square dy. Again you can use the same concept again here, that the h of this parameter, as this is the parameter that we consider for the Ampere circuit law, so this must have a condition that the h must be tangential to this path. So the tangential component or the parallel component of this field to this path is minus 3y square. So you can directly take the minus 3y square also instead of taking the dot product, but you can do you can take the dot product also. Then this will give me the minus y cube in the limits -1 to 1. So for path 1 I will obtain the as the -2. Similarly we can perform this for part 2 also. So the h dot dl2, this will be, this was dl1, this was dl1. So the h dot dl2, you just have to go to part 2, which is from 5 to 2 in the x direction. So the change in length is only in the x direction. That's why the tangential component of the field to this x is only the 6xy. So we can directly write here the 6xy, the dx, and the dx changes from 5 to 2. So if you solve this, we will obtain minus 63 amperes. Okay, now for the part 3 we will repeat the same procedure, that is the h dot dl3. This will, for the part 3 changes from y equals to 1 to y equals to -1. So and the tangential component of the field is again the minus 3y square to the y direction is minus 3y square dy, and the limits are changing from 1 to -1. When you solve this, you will obtain 2 amperes. Now for the part 4, what will be this closed line integral? The line integral will be in the limits, as the limits are in the x direction, that is the x changes from 2 to 4 in part 4. So again it changes from 2 to 5, and the component of the h along the x direction is the 6xy dx. So when you solve this, you will obtain again the minus 63 amperes. Now we will add all these to get the left hand side of the Stoke's theorem. So this will become the left hand side of the Stoke's theorem, which is h closed line integral. This will be equal to path 1 plus path 2. Path 1 was -2, path 2 was minus 63. From path 3 we got plus 2 amperes, and from path 4 again we got minus 63. So at the end this becomes equal to, the left hand side becomes equal to minus 126 amperes. Now let's solve, or let's do the right hand side and see whether we get the same answer or not. So the left hand side becomes equal to minus 126 amperes. Now solving the right hand side, which is the surface integral of the curl of the magnetic field intensity with respect to the surface area. Now let's first talk about the surface area, which is ds. So the magnitude of ds is basically the change in length to the change in width, which is in our case the change in the x direction and the change in the y direction. It is constant in the z direction. So this means we can write this as delta x into delta y in the az direction, or simply dx dy in the az direction. I can write it like this. So coming to now the delta cross h, the del cross h is, we can write the del cross h as the ax, ay and az, partial by partial x, partial by partial y and partial by partial z. To the components of h, the components of h are 6xy. Here you have the minus 3y square, and here we have 0. So you just have to open this determinant, and what we obtain is, for the Ex we will take the determinant like this, which is 0 minus the partial by partial z of minus 3y square in the Ax direction, minus in the Ay direction. What we have this 0 into partial by partial x, which is 0, minus the partial by partial z into 6xy. It means the partial derivative of 6xy with respect to z. And the third component along the z is the partial by partial x minus 3y square, partial by partial x of minus 3y square, minus partial by partial y 6xy. Now further solving this, as this component is independent of z, so this will become 0, so the x component becomes 0, the y component also becomes 0 because this is also not a function of z, and this portion is also not a function of x, so this becomes 0, and we are left with only minus 6x a z, as the partial derivative of 6xy with respect to y is 6x, so minus 6x a z is the what we get as a curl of h. So now we have the ds, now the del cross h is there, and the surface area area vector we have already computed. So what we have is, we can now solve the right hand side, which is the surface integral with respect to x, with respect to y. The del cross h is we have obtained, which is minus 6x a z, and the dot product with respect to the ds, which is dx dy a is dx dy a z. So the dot product of the unit vectors gives you 1. We are left with the limits of the x are from 2 to 5, and the limits of the y are from minus 1 to 1, and we have to solve this now, and we will see what we get. So if you solve this, we will obtain minus 6x squared by 2 in the limits 2 to 5 into the y in the limits 1 to minus 1 to 1, which if you put the values, you will obtain minus 126 amperes, which is exactly the same as we have obtained in the case of the left hand side. So this means that the left hand side of the Stoke's theorem, which is the closed line integral of the magnetic flux density, is equal to the open surface integral of the curl of the magnetic field intensity and we have seen that both sides gives you minus 126. So this is the proof or the validation of the Stoke's theorem. Now coming to the magnetic flux density, so we define the magnetic flux density in free space as this relation, where mu naught is the permeability of the free space. The units are Webers per meter square or the Tesla. Remember, the magnetic flux density was also measured in the older units, which was called as the Gauss or G, and the relation between the 1 Weber per meter square or 1 Tesla is the 1 Tesla or 1 Weber per meter square. This is equal to the 10,000 Gauss. And mu naught, as we said, is the constant of proportionality, and this is equal to 4 pi into 10 raised to the power minus 7. This is not dimensionless. Its unit is Henry per meter. And this relation of the magnetic flux density is analogous to the relation that we have obtained in the case of the electric flux density, that was epsilon naught E. So we are using the same analogy, and we are defining the magnetic flux density, which is equal to the product of the mu naught, the permeability of the free space, into the magnetic flux, into the magnetic field intensity. Now the same way we can define the magnetic flux as we have defined the electric flux. So the magnetic flux is the flux lines or the flux density, the dot product of the flux. So the magnetic flux lines or the magnetic flux equals to the surface integral of the magnetic flux density, and its unit is Webers, and this is the amount of magnetic flux passing through any area. Now this analogy with the electric flux lines, which we computed as the psi equals to the closed surface integral of the flux density, and this is equal to the amount of charge inside this closed surface. So the number of flux lines measured over the surface is equal to the charge enclosed by that closed surface. But is this true in the case of the magnetic field also? No, because in the case of the electric charges we have isolated charges, whereas in the flux lines going out of the closed surface can be different from the number of flux lines going in. So you may have some flux lines, or the divergence will not be zero, as we have seen before also, that the divergence will not be zero. But in the case of the magnetic flux, as we do not have magnetic monopoles, so whatever closed surface you assume, the number of magnetic flux lines going out will be equal to the number of magnetic flux lines going in, as the magnetic flux lines forms loops. So that's why the divergence of, or the B or dot ds, this will give you the surface integral of the flux line. This will give you 0, because the magnetic flux lines are closed and do not terminate on magnetic charges, because we do not have magnetic monopoles, we do not have isolated magnetic charges. That's why this B dot ds becomes equal to 0, and using the same divergence theorem we can say that the del dot B, this is equal to 0, that the divergence of magnetic flux density will always be equal to 0. It means that there is the number of flux lines going out and the number of flux lines going in into the closed surface will always be equal to 0, or in other words, there are no isolated magnetic charges. That's why the divergence will be 0, and this is your fourth Maxwell equation. Now we can summarize these four Maxwell equations as, so now these are the four Maxwell equations. This is in the point form of the Maxwell equations or differential form of the Maxwell equations, whereas these are the integral form of the Maxwell equations. We have discussed all of these, in which we have the del dot D. This we discussed before the midterm exam, that the divergence of the electric field, electric flux density is equal to the amount of charge inside the closed surface. Similarly, the curl of the electric field is always equal to 0 because the electric field lines, electric flux lines do not curl, and the through the Ampere's circuit law we have seen that the curl of the magnetic field intensity is equal to the current density. And now we have discussed that the divergence of the magnetic magnetic flux density is always 0. This is due to the Gauss's law. Gauss's law states that the flux lines going out of the surface is always equal to the amount of charge enclosed by that closed surface. So we applied the same law to the magnetic flux density, and we obtained the divergence of B equals to 0 because the divergence measures the amount of flux lines going out or going in. So as the amount of flux lines going out and coming in to the closed surface is always equal in the case of the magnetic flux lines, that's why the divergence of the magnetic flux lines will always be equal to 0. And this is the proof that the magnetic monopoles do not exist. And with this we conclude our today's lecture. So I hope that now you know the physical significance of, or the physical meaning of the Maxwell equations also. Thank you very much.